Good afternoon. I hope you're doing great. If you can hear me clearly, please type 1. Ivan, Lucas, Nash, Carl, Ali, Atakan, Ronnie, Haidar. Great. I'm going to close my webcam and then share the screen. Okay, this is the add class code. Please keep it for our friends in case they join us later and they want to have that. I'm going to copy it in the chat box. Would you please confirm if it works? Okay, awesome. Thank you very much. You remember the previous session? We almost finished talking about slicing, how we can just send just a batch of pictures instead of sending them all. And then we said that is something when you define batch, it's normally what is happening. These are the things that we started, and we come up with the idea that 0 and 0 starts from top left of the image. Today we are gonna continue saying that the number of samples that we have always is in the first dimension of the matrix that we have. For instance, if we have a 2D dimension, two-dimensional matrix, the very first element, which is called axis 0, is the sample axis. Imagine that in MNIST dataset that we talked about, we said we have, for instance, 60,000 28 by 28. You remember we had that. So the first element would always represent the number of samples that we have. The thing is, in the batch part, you remember we said exactly, Lucas. In batch part, we said, for instance, we could have batch equal to 128. What is happening behind the scene is it is going to take the first 0 all the way to 128, not including 128. And then the next round is going to be 128 all the way to 255, not 256, and so on and so forth. You can imagine that this could be something like 128 multiply n. All the way to 128 multiply n plus 1. N starts from 0. So that is why the first attempt would be from 0 all the way to 128, right? And now we understand why the left side is exclusive. The right side is exclusive because we are going to start from exactly the same. It's going to keep the formula way simpler. So if I ask you, what is axis 0? What is the first dimension in deep neural net? What is your answer? Okay. Anybody else except Lucas? Do you confirm that it is the number of samples? If you can hear me, please type 2. Okay, thank you. So the question is, what is axis 0? Thank you very much. Okay, the number of samples. The next thing that we are going to deal with is the data you'll manipulate in deep learning. Mostly, we deal with either 2D, 3D, 4D, and 5D tensors. This is not very much generalized when we say, for instance, images is 4D, and the reason for that is, what if we don't have any color, for example? So these are samples, not accurate in 100% of the time, but mostly when we talk about 2D tensors of shape, it means something like an Excel sheet. Like we have rows or samples, that's again the first element. And then we have features. Imagine that features could be the columns in an Excel file that we have. The other thing is, if you have time series, for instance, you want to check the price of something today, tomorrow, and next days for a chain store, for example, then you are going to have a list of 2D for today, a list of 2D for tomorrow, a list of 2D for a day after, and then it's gonna make it 3D because you have a time series there. You have a timestamp, right? What could be another example for time series? Anyone has any opinion? Lucas said like weather data, correct? We could have, yeah, we could have speech, okay, audio. How could you say it has 3D? For weather, I can understand because we have some features like wind speed, the type of cloud, the air pressure. So these are the columns that we have. And the output could be the temperature that, or for instance, if it is rainy or not. And we can keep that for different days. So it's gonna be 3D, as Lucas said. But how about the speech? How you can just say speech is a kind of 3D. Just think about it, Ali. If you come up with any idea, please type. Okay. The other example that we could have is a stock market. Like we have, Matthew said, tone, pitch, language. So we have number of samples. That's the first element. We have audio files. It should be a conversion or translation to a bitmap. It's going to be 2D. And then we have labels, right? Okay, for 3D, one very famous example is the stock market. In a day, we have 290 minutes that the stock market changes the values. So we have 290 lines. And imagine we could have just 3 columns like the price, if it is incremented, or these kind of information. But because we are gonna keep that for, sorry, we have it for 390 minutes for 250 days. Yeah, 390 minutes a day and for 250 days. So the number of samples would be 250 out of 365 days that we have. We just have 250 business days. So it could be 1 sample. But for the image, mostly when we talk about the images, we have the color channel. It really depends on the system that you want to apply. But if it is RGB, means you have 3 planes. 1 plane for red, 1 plane for green, and 1 for blue. In that case, you're gonna have the number of samples again, and you have 2 standards. The TensorFlow standards is channel last, means you're going to have samples, height, width, and then the color depth. If it is red, if it is green, or if it is blue. In Theano, the color channel stays first. They call it channel first. Well, by saying first, it means right after the samples. So then we are going to have samples, color depth, height, and widths. Now, the question for you is, why in MNIST dataset that we talked about, we didn't address the channel, the color channel? While I'm reading the answer of Ali, please come up with the answer why we had just 60,028 by 20. So if you convert audio into absolutely. Thank you, Ali. It makes total sense. So in that case, Ali, we have 2D for the audio, right? Based on conversion. And we have samples, correct? So we have, for instance, 20,000 different samples. Am I right? For instance, you say hello, and you're gonna just change it to pitch and then to those kind of bitmap sort of thing. And for each of the samples, for each of the rows, you're gonna have 1 label. In that case, I guess that's the best fit. That's the best fit for 3D, because we are not gonna have. The problem of that is the first voice that you get is like a bitmap, as you said. We need to flatten it, so we change it to 1 column. And technically, we use it like MNIST, and we don't have any color channel, so it's going to be 2D example. Right? Okay, getting back to question that I asked. I asked, what if we get back to the example, the standard example of Hello World. In Hello World example, or MNIST, we had 60,000 samples, 28 by 28. and we didn't say the channel, the color channel. And like I said, because we utilize monochrome, only black and white. In that case, technically, we do not have separate planes or separate dimension for red, green, blue. Just we have one dimension for black and white. Right? Okay. That is correct. Absolutely, Lucas. Let's go to the next part, and for the video. For the video, you can say it's exactly like image, but the only difference is you have a frame. Imagine that you have, well, it's not going to be a very nice video format, but imagine that you have 4 frames per second. Technically, for something that our eyes can tolerate and bear, it should be something like 30 at least, or 24 frame. And for kind of natural move, it should be 60. But anyway, imagine that you just want to have basic form of video. So you take 4 frames. So you have number of frames, and then you have number of you have width and height and color. It's exactly like the channel last in TensorFlow. We have another standard like Tiano, that we have channel first, then width, height, width, and that's it. So there are 2 mechanisms, 2 standards. But what we see here, first we have samples, video 1, video 2, video 3, and so on. And imagine that we have just 240 frames, number of frames that we have. And each frame has its own height and width and the color depth. Okay. We rarely use that, but this format is 5D, and the reason that we still do not use it very much because of time complexity. Okay, so by saying that, we get to know what are the 4 types that we mostly use in deep learning. So for 2D, you said that something like Excel file. For 3D, we said whenever we have a time series, like a stock market. For 4D, we said something like number of samples, width and height, and then the color channel, if you're using TensorFlow standard. And for video, you just need to have frames. So it's going to be samples, frames, height, width, and the color channel. Okay. Now we get to some TensorFlow applications. Technically, whenever I want to show you something that we are going to face in a few minutes later, whatever we see here in this picture, page 44. At the beginning, we have something complex for the computer. So it's going to do some tensor operation in several steps and layers, multiplying by weights plus biases, again multiplied by activation rule. And then it's gonna just get better and better. Imagine that you have 2 papers and you just mix them, and in every step you try to uncrumple and make it clearer and clearer and clearer. Those steps are nothing but some tensor operations. And here we are going to see what is happening behind the scene. Most of the time, we do not use calculations ourselves. We just use the predefined mechanisms that already exist. But to have a better understanding and utilize them better, we just quickly review them. As you see here, it says keras.layers and dense, and we have 512, and the activation is relative. This is nothing but when we have 512 neurons, we are going to use widths multiplying by the inputs plus the bias on top of each column. And then we are going to decide if we are going to use that result or we are going to cancel it. So ReLU is going to decide if it is a negative, we are going to just use 0, means canceling that neuron. If it is positive, we are going to take that number. Okay. The very first thing that we want to just remind here, you're going to see once in a while assert in these formulas. Anybody can say what is assert? Test. Good. What does it mean? Mm-hmm. Exactly. That's absolutely right. Let me bring a tensor. Hopefully it's gonna, yes, there we go. Exactly. So let's just run this together. Imagine that x is equal to string hello. We check if x is equal to hello. Look, it's not gonna do anything. But we check if x is equal to goodbye, so it is not. So it's going to raise assertion error, means this is something that we didn't expect. We mostly use that for checking the condition or conditions that are essential to proceed our procedure. Let's look at an example. Here we want to have a simple version of ReLU function. For doing that, we say, okay, is the length of the shape is 2? Means, do we have 2 dimension? Do we have a matrix? If yes, so continue. Else, we are not gonna just go through the process and we raise an error. We say for every single eye that we have in the shape dimension 0, means for every single row, go to, then we are going to have a nested loop. Go to every single j, means every single column, and see every element that we have. Pick the maximum value of that element or zeros, means that if the max is 0, if we have a negative number, so the max of negative number and 0 would be that 0. Else, we have 0 or above, then pick that number. Does that make sense? Okay, for the sake of just one example, if you see here, just these three cells have negative values. So if I apply that, these three are gonna bring 0. The rest would just keep whatever they have. Okay? Again, for every single I or row, go to every single J or column, and then pick means this one. Then next J, next J, next J. When we are done, we go to the next, and we get that. If it is 100% clear how ReLU works, please type 2. Thank you, Algor, Ozan, Joai, Zoe, Julian. Yeah, that's absolutely correct. And it brings non-linearity to our calculation. Okay. You remember we said that on the left side we have a picture, right? Some pixels. And we do some calculations like multiplying each neuron by weight, adding bias, and we try to transfer to the next layer and next layer and next layer. If you just have AX plus B, it's going to be a linear transition. We want to have non-linearity in our equation. ReLU provides that non-linearity. You might say, why this one is the best? We didn't come up with that idea day number 1. They tried different nonlinear functions like sigmoid, and just ReLU, because it worked better, they picked that. So it is going to cancel some of the neurons and make it, yes, nonlinear. Exactly. That is correct. Absolutely. Okay. Can you elaborate on the last sentence a bit more? I don't want just to confirm it. It sounds correct, but I want to make sure. Okay, meanwhile that Lucas paraphrase his last sentence. Let's see. These operations are available as well optimized built-in functions. Look at this one. For ReLU function or for something like addition, technically you see here we have used 2 nested loops. This is just for us to imagine how it works. But in reality, we don't have nested loops because the performance is super low if we just make this one like actual nested loops. Imagine you want to add two values together. What it does here, first it checks if the length of x, the length of x shape is 2, means it is 2-dimension. You can use ending instead of saying length of x dot shape is equal to 2. And it says that if the shape of these two are equal, so it means if x is, let's just show x by orange and y by blue. So if these two have the same number of rows, like 3, and the same number of columns, like 4, then you can just pass these two and then get to the calculation part. We get a copy of x, and then we say for every I in the range of rows, because x dot shape is talking about the number of rows. And you might ask, why not x dot y dot shape? Because they have the same dimensions. There is no difference. And then for j in range of x or y, dot shape means any column. Just pick that element. Just pick that element, for instance, this one. Pick that element and add it to the current value of, which is going to be this one. So 1 plus 1, it's going to make this 2. That's a new x. Then we are going to go to the next j. So 2 and 2, this is going to make this one 4. Then 3 and 3, it's going to make it 6. And 4 and 4, it's going to make it 8, right? This is actually what is happening here. It said that technically these operations are available as well optimized built-in NumPy functions. We do not use that mechanism. You just say x plus y, and it's going to automatically add them together in a very linear form. You don't need to go to a kind of 2-dimension. The other thing is simply you're going to say, let's have z, which could be 2, 3, n-dimensional matrix. Then you're going to say, just bring me the maximum of each element and 0, right? Okay, up to this point and moment, if everything is clear, please type 5. Thank you very much. The next part that we have is about broadcasting, and let's just consider broadcasting in this picture for a sec. So broadcasting is simply a set of rules for applying binary U functions, universal functions like addition, subtraction, multiplication, and any other things. Please give me a second. I want to change the screen that you can see. Please look at this one. If you have something like 1, 2, 3, and this is your x, and you want to add this one to something as simple as 10, 20, and 30 as your y. This is very simple because you know you are going to just use the first and then the second and then the third respectively elements. So the result of these two is going to be 11. The result of these two would make it 22. And the next one is going to be 33, right? There is no problem for such a cases, but what if you have something like 1, 2, 3, 4, 5, 6. In here, how many rows do we have? 2. How many columns do we have? 3. And you want to add such a thing to 10, 20, 30, which now we know that it has just 1 row and 3 columns. The general rule is if we have this similarity in one dimension, which is going to be the number of rows in this example, and we have 1 in one of the matrices, then we can increase that matrix that contains 1 in this similar item, and we just duplicate the values, and it's going to be fine, right? Guys, is it super clear so far? If yes, please type 1. But the problem happens, thank you very much. The problem happens when we have something like 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 3 here. But in the other side, we have 10, 20, 30, and 40, 50, and 60. So this one, we have 2 rows, while 3 columns. In this one, we have 3 rows and 3 columns. The problem arises from this portion, the dissimilarity is in here. But because no one is 1, we have ambiguity or not clarity in increasing the number of rows here. Why? Because we are not sure, should we consider the minimum, like this row, and duplicate it here? Or should we consider the maximum? Or should we consider the average, or what? For such cases, it is not possible to broadcast. So please just take a quick look at these samples that we have. Let me just bring back to this place. Imagine that here we have 1 row and 3 columns. Here we have just a scalar. So whenever you have a scalar, means no dimension. So you're going to just add 1 into the left side, and then you just increase that. And it's going to be like, you know, just like stretching this to have the same number of columns here. The same applies to this one, which we have a matrix of 3 rows and 3 columns, and you're going to stretch it like that. Even if you have just 1 column here and 1 row here, but you have 1, which belongs to number of columns in the left side, and you have 1 in the number of rows, you can just stretch both of them to make them equal in terms of number of rows and number of columns. But imagine if on the last example, in Y, we just had 2 rows instead of 1 row. We were not sure. Should we consider the maximum of 2 rows or minimum or average or what? Then because of that confusion, you could not come up with a kind of a straightforward answer. Is it clear, guys? If yes, please type 2. If you have any confusion or question, please ask your question. Among the concepts that we have in chapter 2, if we have 3 topics that could be a little bit challenging, broadcasting is one of them. So let me read the regulations that we have here for broadcasting, and that is why I use another reference to just make sure we covered completely. If the 2 arrays differ in their number of dimensions, means, for instance, here we have 2 dimension, right? Well, technically, we could say 1 dimension and 0. If we have different number of dimensions, then what are we gonna do? The shape of the 1 with fewer dimension is padded with 1 on its leading or left side. So what is the number of dimension here? Guys, here we have 3, 3. Here we have just 3 columns. This is a kind of vector. So we are going to say 1, 3. We pad. My apology. Here we have 3 times 3, but here we have just 3, right? We are going to just pad as it said 1, so it's going to be 1, 3. We pad it to the left side, that's what it said. On the left side, if the shapes pad with 1 on its leading left side, if the shape of the 2 arrays doesn't match, so now the shapes are not matched in any dimension, the array with shape equal to 0, we are talking about this one now. We are going to increase that to the number that we have maximum in the other one. So to the array with the shape equal to 1, that dimension is stretched to match the other shape. And the problem happens when if in any dimension the size disagree and neither is equal to 1, an error is raised. And we just talked why. Let's get back to continue. So here it says that what happens with addition when the shapes of 2 tensors being added differ. When possible, and now we know when it is possible, and if there is no ambiguity, and we know when ambiguity could happen, the smaller tensor will be broadcasted to match the shape of the larger tensor. Broadcasting consists of 2 steps. One of them is the axes, or called broadcast axes, are added to the smaller tensor to match the number of dimensions of the larger one. So this means that if we have 1, 3, we are going to just match it with the maximum one. The smaller tensor is repeated alongside. You see that the smaller, which is number of rows, is repeated alongside these new axes to match the full shape of the large tensor. So in terms of implementation, technically, we are not going to implement it like this. If it was like that, it would be horrible because we use, again, 2 nested loops and the order would be N2. The big O would be exponential. whenever we say one algorithm is in exponential big O, it means that algorithm is inefficient. We just show that here, and we are gonna just consider that tomorrow, how this one works, and we continue our journey saying about all these things, knowing that it's not gonna do exactly like this one. So please just, if it is a little bit clearer, because just I saw 4 of our team members mentioned that they got the whole point. This time, if it is a bit clearer reading this time, please type 3. Parsa Alvaro. Friday, thank you. So before we terminate the session, I would like to ask you, please go to, just give me a second. I want to make sure that if it is already set. Please go to the course and the assessment. And please confirm if you can see quiz number 3 now, if it is visible. If you just got there, refresh the page. Okay, Ronnie, thank you. Lucas, merci. Okay, everybody, thank you very much. I do appreciate. I wish you the best of the rest of your day, and see you tomorrow. Have a wonderful one. I close the recording and have a good one. Ciao. Bye. Bye.